Okay. Oh, it turns itself out. It turns itself off after every half an hour. Okay. So I was just saying that if you're not doing this on your feet in front of a camera, you use Stirling's approximation. But if you are, then you just use the fact that you look. So n factorial is defined as n times n minus 1 times n minus 2 times 4, 3, 2, 1. Okay. So how many terms are there in here? There are n terms, at least n over 2 of which are at least n over 2. So this means, it's actually, yeah, at least n over 2. So this means that this is greater than or greater than or equals. I'll say greater than or equals just for safety. I think it's greater than, but this is greater, at least n over 2 to the n over 2. So log of n over 2 to the n over 2 is n over 2 log n over 2 equals n over 2 log n minus 1 n over 2 log n minus n over 2, which is big omega of n log n. So that's a lower bound. This is where we use big omega. We want to say, okay, how many comparisons do you need in the worst case? At least for sufficiently large n, you're going to need, okay, there exists an n0 and a c such that for any n0, for any n greater than n0, the number of comparisons you're going to need in the worst case is going to be at least c times n log n. Okay? Which is what we learned in the previous lecture. So I think that's all I actually wanted to say today, except for the quick select. So I have 8 minutes to do quick select. I can sketch it, and then it can go in the scribe notes, maybe. Vote. Do people want to see the analysis of quick select? Is anyone listening? Oh, okay, good. So, no, if the 8 minutes isn't enough, I mean, we're a bit behind already. It's just going to have to go in something else. Okay, but it's, so I can sketch the idea. So the problem is, you need a little bit, for the sake of whoever is doing these scribe notes, would it be possible to take a picture of the board? This is, you didn't see this. This is, I went out and bought a camera yesterday and a tripod. And the camera, that's why I came around, because the camera turns itself off after half an hour. So I actually gave the iPad away. I gave it to one of the TAs who was having technical difficulties, because she's much better at computers than I am. With computers. Maybe not at computers. But okay, So the iPad was sufficiently high resolution. I hope the camera is sufficiently high resolution. Yeah, the low resolution is the webcam, but the webcam is not. Oh, 5 minutes. Okay. But we have a nice big whiteboard now. What is the idea? So remember, for quicksort, we just say we want to bound the depth of we consider some branch and we say how deep is the leaf at the end of that branch. And all we have, because we know that each level of the tree, we've got, if you sum up all the little subarrays you've got at that level, their total size is n. So you can bound the total work you do by n times the height of the tree. And so if you can argue that the height of the tree is order log n, then you're done. The problem here is quick select uses linear time, because you say, okay, what happens? I'm going to look at the array, I'm going to choose a pivot, and then I'm going to split the array. If I, split it roughly in half, and then I know which half contains the element I'm looking for. Yeah, I hope this is going to work. I mean, I'll send a picture because the laptop and the camera are currently sitting on my mini ironing board, which is sitting on my drying rack. It's a super low-tech solution. Okay, why that doesn't work? So in the case of quicksort, we just wanted to say, okay, so if we get a success, if we split the thing roughly into half, so if we're in the middle half of the array where I split, and not in the first quarter or the last quarter, that's a success. The problem is with quick select, if you consider that, now you're only doing one branch. But the problem is, now it's not enough to say that branch is probably short, because it's probably order n log n, because what if you had a lot of failures at the beginning, and then you had successes? So if you have like log n failures, if you're doing linear time for each of these, that's going to give you n log n again. And you don't want n log n. You want order n, right? Because if you're doing n log n, you might as well just sort the whole array and then pick out the element you want. So in the book, it actually also gives you a worst case algorithm for finding. So instead, just to sketch this, what you're going to do is consider the first. You're going to take the first split, and you're going to pick a pivot, and you're going to split. And now you say, well, I'm going to give you a slightly different algorithm than quick select. So right now you're going to have this really demanding quick select, and it says if I split it in the middle half, then it's a success, and I keep going. If I don't, then I just start over. I start over again. I put the stuff back together, and I pick a new pivot. So this cannot be faster than quick select. So if we can bound this algorithm, if we can show that this algorithm is linear time, then quick select is also linear time. And so remember that each time I split, I get a success with probably 50%. So what is my expected work on that first split? Now this is expected, but it's still going to give me overall a with high probability bound. So it's going to be, with probability half, I'm going to, so I'm going to pick the pivot, I'm going to pick the first pivot, and I'm going to do linear work. So it's going to be, what is my expected work? So it's n, and then maybe my first pivot was bad, it was a failure. It's a failure with probability a half. So it's a failure with probability of half, and then I have to do another n work. I choose another pivot and I repeat. Okay? And then maybe my first pivot gives me is a failure, and my second pivot is also a failure. That's with probability a quarter. And then I have to do pick another pivot and split. Okay? So this is plus. So maybe I have to keep going, but the probability of getting a lot of failures is small, right? So this is 2n. Okay? So the expected work I do for the first split is like 2n. Now, so at the next level, how big is my array? Well, it's at most 3/4 n. Okay? So now I'm going to go for the second level. And I'm going to say, okay, so I definitely do 3/4 n. And then, with probability of half, so I pick a pivot, I do my split, and then if it's good, I'm happy, and if it's bad, I do it over again. And then I'm going to get a half times 3/4 n, and so on. And so this is going to give me 2 times 3/4 n. And then at the third level, I'm going to get 2, so then at the third level, it's going to be 3/4 squared n plus 1/2 3/4 squared n plus, right? So at each level, that's how much work I'm going to do. And I am now out of time. So the thing is, the trick is you view these as random variables. Okay? And then you sum them. So if you have these random variables where this is x1 and what